Hello, my name is Christian Eskert. I am a student at Southern Nazarene University, and my research is over arbovirus surveillance in Oklahoma. And my mentor for this project was Dr. Franzo. So for some background, mosquito-borne diseases have increased recently in the past decades in the United States, and the most common of those being West Nile virus, which affects 7 million people per year and costs about 56 million for to treat hospitalized patients. So for the transmission of West Nile virus, we have birds, which are your amplifiers. And so when a mosquito that's infected will bite a bird, any mosquito that's not infected that bites that same bird will now become infected. And then we have what we call dead end hosts who do not amplify the disease, such as mammals, um, who, when they are bitten, they do not add to the amplification. Once you get bit and have West Nile virus, a non-infected mosquito will not become infected after biting you. And so West Nile virus is an endemic seasonal zoonotic arbovirus. It's seasonal and it can be transmitted from animals to humans. People of ages 50 and higher and compromised immune systems are at highest risk. Most commonly, symptoms include fever, and symptoms such as like a cold. In rare cases, you can have encephalitis, paralysis, and even death. And currently, there are no vaccines, and only basic care is available. Here we have the spread of West Nile virus from 1999 in New York to 2004. And this is just in a 5-year span where it spread throughout the entire U.S. And below we have human cases in Oklahoma with outbreak years in 2003, 2007, and 2012, which were each hotter and drier than average years. So throughout the span, we had 814 cases with 58 deaths. And you need to keep in mind that many cases go unreported, as many people don't even show symptoms, and many who do show symptoms aren't even aware that it is West Nile virus. And one thing that's important to note is the mortality rate in Oklahoma is higher than the national average at 7.1% compared to 4%. So here we have our locations of our trappings, which are the red dots. Here we have our objectives, which was to determine mosquito diversity, abundance, and to test them for arbovirus. Here are our methods. We would trap the mosquitoes, identify them, extract their DNA and RNA, then run the RT-qPCR. If that came back positive for flaviviruses, we would run a gel electrophoresis with West Nile virus specific primers to check for West Nile. Below is our 3 traps in order of, you could say, usefulness. Here is our homogenization tool with the beads, and then we added the mosquitoes. We would blend them up and then centrifuge them to remove the liquid on top and not to take in any of the solid. Here we have the mosquito distribution by species, with Aedes vexans being the largest portion, followed by Culex tarsalis, Culex pipiens, Ginkgo fasciatus complex, and then Aedes tributatus. And then below is mosquito distribution by species throughout different trapping locations. And as you can see, it varies greatly depending on where we trapped. At the bottom here is our PCR and gel electrophoresis showing positive samples at 265 base pairs, which is these 4 pools. We had a negative, which was DI water, and a positive synthetic sample. Overall, for our results, we trapped over 3,200 mosquitoes with over 130 trapping events from 18 different species, which we had 24 pools test positive for flavivirus, 9 for alphavirus, and then 4 for West Nile virus. So in conclusion, the most dominant mosquito was the invasive Aedes vexans, which accounted for 37% of our total mosquitoes. And for future work, our goal is to screen for different types of viruses and to be able to detect the viral genome in our samples. And below is my references and acknowledgements. Thank you.